So here we are, folks, on lesson 41, the Quantum Electron Cloud model. And you know what? I'll forgive you if you kind of forget about this one. Because when people get to the point where we have the Bohr model, it's almost like you want to say, okay, we're finished. We're done. We're okay. Because if you think about the way that things are presented to you, even in, let's say, a high school chemistry class, the Bohr model is the way to go. And it works, it gets the job done. But here's what we have to remember: just because it's good enough doesn't mean that it's great. And there's nothing wrong with using the Bohr model in the way that you are in high school to figure out some stuff. And in fact, if you go on to university chemistry, you'll keep using the Bohr model. You're going to do some modifications to it. You'll learn to hate SPDF orbitals, but still, it's the Bohr model. But what we have to understand is it still isn't the best. And that's where we get to this, the quantum electron cloud model, because even in the time period of Bohr and Bohr's model, they knew that there were problems. In fact, more than one. So what we can look at is, first of all, that it still didn't explain why electrons wouldn't be emitted or wouldn't emit EMR when they were spinning around their energy levels. Bohr kind of hoped that just having an explanation that fit other evidence would eventually lead people to figure out something else that would explain why these energy levels were stable, and almost like you could ignore Maxwell in those positions, which you can't. So it's not helping us with that. It's not leading us to the next answer. Worse than that, it only works for hydrogen. Go back to all those formulas you just learned, all this stuff we talked about, and damn, it only works for hydrogen. The crazy thing is, if you do like emission spectra with other gases and stuff, you still see lines and everything, but none of it fits those formulas. And it's not just like we have to replace Rydberg's constant for hydrogen with another constant. No, none of those formulas work. It all falls apart. Then, even the emission lines themselves betray us. As equipment got better and better in that time period, they were able to kind of think of it as zoom in on the emission lines. And what they noticed is what they called the fine structure. A line was made of hundreds, if not thousands, of really, really closely spaced lines. Now, the issue with that is it means that the jumps aren't exact. It would sort of be like going back to the analogy that I used when we did the Bohr model, that, you're stepping up and down stairs and you can fall down this many stairs, or, stuff like that. Well, here, it's almost like you would be standing on the fourth step, sort of. Your foot could be a little higher above it. You're floating above the fourth step a bit, or somehow your foot is sinking through in below the fourth step a bit before you do your tumble down to the second step or something like that. That's the only way to explain the fine structure, because it's little changes, little differences in the amount of energy that would be released from slightly different sized jumps. Finally, those emission lines, some of them are brighter than others. You might remember I said when I talked about the emission spectra for hydrogen that, there's a few other colored lines that you could maybe see, but they're very faint. Yeah, that's because they're really hard to see. The red is really super bright. And then the bluish green, you can see it, but it's not nearly as great. And then the violet, and then a few violets that kind of come after it, very, very difficult to see. If the Bohr model is working kind of the way that we would like it to work, all of those emission lines should be the same brightness. So, what are we going to do about this? Well, we have to ask the question then of what did Bohr miss? Kind of like when Rutherford had his problems, Bohr asked, hey, what can I do to fill in for the problems Rutherford had? Now we have to look at what Bohr missed. And definitely, Bohr is actively involved in coming up with this new model, but there's a bunch of other physicists also, and it becomes more collaborative, and that's why there's not a single name associated with this model of the atom. So, what's the big deal? Well, Bohr was still treating electrons like they were particles. And you say, yeah, they are particles. Oh, but wait. De Broglie had shown us how particles can have wave-like characteristics. So maybe this is part of wave-particle duality. And this is important because maybe what we should be thinking is that if we're going to use quantum mechanics, we can't pick and choose the parts we want to use. Bohr basically picked the idea of energy in discrete pieces, but he never thought of all the other quantum-y kind of stuff, like de Broglie wavelengths. And we can't do that. We're either using quantum or we're not. And definitely when we're talking about little teeny tiny electrons bouncing around through energy levels, we are definitely at the quantum scale of things. We should be using quantum ideas. So, what I need you to do is imagine bending the equilibrium line of some waves into a circular shape. What do I mean? Well, first think of this diagram, where what I'm showing is a straight line that's the equilibrium line. And then starting on the far left, we've got 1, 2, 3, 4, 5 wavelengths. Each wavelength is a complete crest and trough. And there's 5 of those. So these are 5 wavelengths. Now imagine I could grab that straight line, like maybe it was made of material that's bendy, and I fold it, I bend it all the way around so the two ends touch each other. I get a diagram that would sort of look like the one on the left, where if you look at it, that bended equilibrium line is the dotted line, and I still have 5 crests. You can point them, or you can count them pointing up above, and I have 5 troughs sticking underneath that dotted line. This is still 5 wavelengths. It's a whole number of wavelengths bent into a circular orbit shape. That's what the electrons would do. They would exist as waves, not particles. And in this particular example, the one on the left, I'm showing the 5th energy level. How do I know that? Because there's 5 wavelengths. I can see 5 crests and 5 troughs. And it's completed. It wraps around and connects with itself. The diagram on the right doesn't, because I have a different number of wavelengths there, and I made it smaller, and they don't bend around and connect. So it's kind of like on the left, I've got something stable, and on the right, I've got something where the waves can't match up with each other, and it's not stable, and it simply won't exist. So the only way to get these stable energy levels is to imagine them as being a bent around whole number multiple of the wavelength of the electron as it's going around that energy level. It can't be a little smaller, it can't be a little bigger, it has to be exactly that size. Now, please excuse the one very crude drawing that I have there, because I was doing it freehand and I know it doesn't look great, but I'm showing you the 3rd energy level, which is a little bit smaller because it only fits 3 wavelengths, 3 crests and 3 troughs. I'm showing you the 2nd energy level. It's definitely got 2 crests, and then the parts that are on the left and right sides, those are the troughs. And even the 1st energy level with 1 crest and 1 trough. And I know it looks kind of weird wrapped around that way, but that's what it would look like wrapped. All of these are stable in the kind of Bohr way of thinking about things. And as long as we're jumping ahead to the quantum electron cloud model, where we're imagining the electrons as waves, it all kind of meshes together. Those circumferences, by the way, are the circumference of the circle is always equal to it being the nth energy level times whatever its wavelength is. So that means we can do stuff like calculate things like the velocity of an electron in its 5th energy level. Now, we do have to have access to all the formulas we were using in the last section. So if you need to look back at those, great. And if I was asking you to do a question like this, I would give you those formulas and constants because you would need them. So let's figure out what we can do to get that velocity. First of all, let's calculate the radius of the fifth energy level. I grabbed the formula that we had before. I put in 5 as my fifth energy level. Don't forget to square it. I put in the radius of the first energy level, and I get the radius of the fifth energy level. So there it is. Now I know that the fifth energy level can only exist when there's 5 complete wavelengths in it. So I can figure out its circumference, because circumference itself is c equals 2 pi r. I'll put in 2 times pi times that radius I just figured out, and I get 8.3053 times 10 to the negative 9 meters, but that's the circumference all the way around. And I'd much rather know what just one wavelength is. In the fifth energy level, that circumference, that number right there, will have 5 wavelengths to be able to wrap all the way around. So I'll just take it, the number I just got for circumference, and divide by 5. This formula isn't on the data sheet, but it's more of a relationship you're expected to remember, that the circumference in any energy level of the quantum model is the nth number of wavelengths fitting into that circumference. So I took the circumference we had, divided by 5, and I've got the wavelength. Now, this, up to this point, still feels very much like the Bohr model stuff, and okay, the circumference thing is from this section, but this is where a person quite often will stop. I have a wavelength, so how do I get a velocity? Well, I would say de Broglie, anyone? I'm going to remember that in de Broglie's way of looking at things, we can basically show that the momentum is equal, in sort of the classical sense, P equals mv, to our quantum way of thinking about momentum of EMR, P equals h over lambda. I stick those two together and I solve for lambda, usually to get the formula I'm showing there, lambda equals h over mv. And if that's kind of baked into your head, fine. But really what I need to do for this question is solve for v. So if you rolled it back a couple of steps and you were just kind of dividing by m on both sides, you would get that formula v equals h over m lambda. I'm going to use regular Planck's constant because I have no reason not to. I'm going to use the mass of the electron. I'm going to use the wavelength I just calculated up above, and I get 4.38 times 10 to the 5 meters per second. And guess what? If we actually do experimental checks on this, that's the velocity of electrons in the fifth energy level. The quantum model is correctly predicting what we observe. But it's got to be better. It's got to be better than just this. And it is. Because this explains why the electron won't emit EMR and spiral into the nucleus. We finally got rid of Rutherford's problem, which was really still Bohr's problem as well. You see, we're now treating the electrons themselves as EMR because they're standing waves going around the nucleus. They're not charged particles anymore. Maxwell only ever talked about charged particles accelerating to produce EMR. If it's already EMR, if we're treating it as a de Broglie wave, EMR doesn't have to release EMR. It already is. So it's stable. The other great thing is I can spin this up to every other element on the periodic table. And that's because if I have something like helium, I'm going to have an extra proton added into the nucleus. That pulls all the electrons in a little bit tighter because there's more electrostatic force pulling them close. That makes it a smaller orbit, and that changes the velocity. And as soon as I start changing all that stuff, everything else falls into place. And all the other energy levels for any element on the periodic table work just fine with this model. Everything's great. So what we've basically gone through in this chapter is starting in 1803 with Dalton's solid sphere model. Atoms are indivisible elements. That's really what he's going with, a very chemistry way of thinking of things. And because we didn't have anything better to replace it with, we got a long stretch until J.J. Thomson comes up with his plum pudding model based on all of his great discoveries with electrons bopping around in cathode ray tubes. But that doesn't seem to quite work because if we use well, I should say because of Millikan's oil drop experiment, but Millikan shows us the way to get charge and mass for those electrons. But if that's all that's going on, it doesn't fit with what Rutherford sees in his gold foil experiment. So he comes up with his nuclear model. But it shouldn't work because the electrons should be spiraling into the nucleus. So Bohr says, ooh, energy levels, very special. Don't have to worry about any of Maxwell's stuff there. But he can't come up with a reason for explaining why that would be the case. And he has all these other failures. So about 12 years later, we get the quantum cloud model, which is now the accepted standard for the closest we can say what reality is really like. Now, the first Dalton solid sphere model is still stuck in the era of classical physics. By the time we get to Thomson, though, we are in the modern era. We have the birth of quantum mechanics. We have Einstein popping up and doing all of his stuff. And so all of these new ideas reflect how we have to integrate those in to have something that works. Now, is the quantum electron cloud model the end? Maybe not. But for like 100 years, it has withstood every challenge against it. And it always comes out on top. It's part of our basic understanding of the structure of matter now. Hope this helps you out. Have yourself a good day.